Every week on Technology Untangled, we try and take a tech innovation and make it understandable and relevant to the regular organisation. But with quantum computing, that's a little tricky.
Once you've loaded the data, you've got to go let it go out across all its universes, do the calculation, and only when it's done can you look at it, and you've destroyed it at that point, but you've hopefully got the answer that you wanted.
Yeah, so quantum computing research is making headlines and seeing record investment, so naturally organisations want to know what all the fuss is about. But when you try and make sense of what's going on, you run headlong into pure maths and complex quantum physics. In today's episode, we enter the multiverse of quantum computing, and we're going to be covering the key concepts that you need to know in order to answer a few important questions. What is the important difference between a quantum computer and a classical computer? Do quantum computers really exist? And why are they so hard to build? What would you need to use a quantum computer for anyway? And which part of all of this is relevant to the average organisation? All that and absolutely nothing more, believe me, that is enough as it is. I'm Michael Bird, and this is Technology Untangled. Quantum computing is a challenge to wrap your head around, and for the purposes of this episode, and mainly for my benefit, we are going to need to oversimplify some of those concepts. So any scientists listening, cover your ears. With that said, let's kick off with our first important question. What are quantum computers, and how do they differ from classical computers?
So quantum computers leverage the properties of entanglement and superposition to perform computations, simulations, and optimizations much, much faster than the classical computers we use today.
Whoa. Okay, we've gone straight in with the entanglement and superposition. Let's wind it back a little bit. And to help me get my bearings, I asked Tony Stranack, Chief Technologist at Hewlett Packard Enterprise, to help bring it back to basics.
There were two thoughts that led to modern day computing, if you like. You've got the name that everyone's familiar with, which is Alan Turing. And what he was trying to do was crack the Enigma code and look at encryption and how do you break encryption using a machine to automate that repetitive process of trying different numbers to see which one worked in order to break that code. And there was another chain run by another guy called von Neumann. And actually his train of thought was more around understanding how ballistics worked. His style and his approach was very much around making the programming very simple and having the hardware do a lot of the work. Whereas Turing, in this massively parallel, actually there was a huge amount of complexity in the programming. Now, as it happens, it was von Neumann's approach that led to this concept of a CPU, an arithmetic logic unit, and that classic architecture that we have today. Turing's approach actually didn't really catch on till we get to quantum computers.
The most powerful classical computers today follow on from von Neumann's train of thought. To double the amount of compute power, we need to double the amount of processors, leading to bigger and bigger supercomputers. On the other end of the spectrum, as materials have advanced, components have got smaller and smaller. But it turns out there's a lower limit on that too.
Strangely, in the classical computing way, which is kind of silicon-based logic gates and how small can I make these things, and the smaller I can make it, the more I can get into its space. Now, as we're getting down to the point where we're getting to the atomic scale, it gets tricky to make them any smaller because of quantum effects.
On an atomic scale, we start to see quantum effects, which is exactly what researchers are trying to harness in quantum computers.
Now, with the power of quantum computers, instead of doubling the number of processors, you just have to add one more bit and you get double the amount of power. So it's much, much easier to scale a quantum computer, if you can build one in the first place, than it is to scale a classical computer, supercomputer, where you just need more and more compute engines to give you the increasing power.
So, if I had a quantum computer and a supercomputer with the same amount of compute power side by side, in theory anyway, the quantum computer would take up a fraction of the space. That's because to double the power in a quantum computer, I just need to add 1 bit. The reason for that is because of a quantum phenomenon called superposition, and it's key to understanding why quantum computers are different. Fans of the Big Bang Theory might remember Nobel Prize-winning physicist Erwin Schrödinger. But if you don't, here's a quick recap.
Schrödinger came up with this thought experiment called Schrödinger's cat that said, if I put a cat in a box and I have some random means of killing that cat, so it'll release poison at a completely random time, I don't know when it's going to do it, I don't know whether that cat is alive or dead at that particular moment. The only way I can discover if that cat is alive or dead is to open the box and go and measure it. He said, in a quantum world, we can't see if that cat is alive and dead. Therefore, it is alive and dead at exactly the same time.
So that's superposition. Important quantum mechanics idea number 1. Electrons, photons, or things on a subatomic level have the ability to exist in more than one state. In a classical computer, we have bits that can be zeros or ones. In quantum computing, we call them qubits, and they can be both 0 and 1 at the same time. So, how is that useful?
I'm going to link back to what Turing was trying to do. He wanted to parallel process as many numbers as he possibly could so he could find the right combination that would decrypt that message. So now if we think about bits and representing numbers, so if I have 2 bits, and in classical computing world they can be 0, 0, they can be 1, 0, they can be 0, 1, or they can be 1, 1. Now, that's the only combination they can be, and they can only be one of those combinations at any one time. Now, in the quantum world, because of this magic stuff that goes on, those 2 bits can actually be all of those numbers at exactly the same time. So if you're trying to decrypt a message and you want to factorize this really big number to find out the 2 bits that will come together and enable you, if you're just going through, and I'm going to repeat, I'm going to try the next one, try the next one, try the next one, in the quantum world, you try all those numbers at exactly the same time. And the more qubits that you add, the more parallelism that you get.
Okay, got it. I think. Most classical computers are limited to doing one thing at a time, i.e. serially. So the more complex the problem, the longer it takes. A quantum computer can parallelize the problem. It can try all of the combinations at the same time because of a very weird thing called entanglement. Important quantum mechanics idea number 2. If you have a pair of qubits that are entangled, they both exist in a single quantum state. What that means is changing the state of one of the qubits will instantaneously change the state of another one. And that will happen in a predictable way, even if they're separated by very long distances. I am heavily paraphrasing here, I might add, and researchers still don't know how or why entanglement works, but it's the reason why adding extra qubits to a quantum machine exponentially increases the calculations it can do, which is pretty cool. But what's that actually useful for? I mean, what's the point in a computer that can do exponentially large calculations?
The problems that we're going to fix are the ones that need this scale, whereby in order to increase the processing power, I don't have to double the amount of compute. I just have to add 1 more qubit. Are you familiar with the traveling salesman problem? Because if you speak to a quantum scientist, he says, this is exactly what it'll fix. It's the fact that if I'm a sales guy and I have to go around all my customers and they live across, let's say, 15, 20 different cities within the UK, this sales guy would have to work out his optimal route to go around those cities. And you could put in the prices and the different costs of travel between those cities and the distances that he'd have to go. So he wants to work out the shortest, cheapest route. That is actually a really, really challenging problem, because you sit there and go, if I use this one first, where does it calculate? Where do I go next? And I have to calculate all the multiples of those cities. So each time I have to calculate all the multiples and all the multiples and all the multiples. It's a bit like the grains of chess on a chessboard. And that is a really hard challenge for classical computing, because it just requires raw grunt. It's those kind of problems, those scaling problems, which each time I add one more city, multiply the complexity of that answer drastically. It's those kind of parallel problems, because actually just adding another city is potentially just like adding another bit or qubit in those worlds, just another combination. And I can try those combinations in parallel. It's those kind of hard problems that scale logarithmically.
So there are a few areas where quantum computers might be useful. Airlines that want to simulate flights and fuel economy, financial market modelling, weather prediction and interpretation, building and simulating chemical compounds. The potential use cases exist. But do quantum computers exist? To find out, I called up Ray Beausoleil.
My name is Ray Beausoleil, Senior Vice President at Hewlett Packard Enterprise, and I direct the Large-Scale Integrated Photonics Lab for Hewlett Packard Labs. I'm a fake Senior Vice President and manager and everything else because I'm really a researcher. So don't be deceived by those other titles. The thing that really matters is that I'm in the trenches with my team. We do research together, but I have to manage the budget. That's my penalty for being the lab director.
So what is the current state of quantum computers? Do they exist today?
Well, it depends on what you mean by existence. I'm going to try to avoid sounding like an existential poet and instead say that we've gone from simple, straightforward demonstrations with a few qubits in the lab to a genuine attempt to start scaling up to larger number of qubits in companies, both large and small venture-funded organizations. And they're attempting to demonstrate larger and larger number of qubits that have been harnessed to do useful quantum computations. But at this point in time, there aren't any hardware platforms that are capable of realizing the promise imagined ultimately for quantum computers. The qubits tend to decohere more rapidly than is desirable, and the gates aren't as high fidelity as we would like them to be. But these are engineering problems that are being addressed very seriously by the various proponents and engineers and technologists.
What makes it so hard at the kind of scale that you're talking about? What are the engineering challenges?
So I think the right way to think about this is that human beings, as far as we can tell, do not exist in the quantum universe per se. I mean, we do in a trivial sense. But the quantum part of existence, the quantum part of reality, is abstract and is not something that we are capable of directly experiencing in a personal way. And so what we have to do is build probes, if you will, that don't have to go to the far reaches of the physical universe, but instead that are capable of reaching into the quantum part of the universe and seeing how it behaves. It's very much like making a souffle, all right? So you create an experiment with your hands, which are classical, using materials that are classical, for the most part, with a qubit, like a single atom, for example. And then when you actually put the experiment into the quantum oven, you are essentially trying to seal it off from the classical part of the universe so that it can do its quantum thing. And if we try to look at it while it's doing its quantum thing, you open the oven door and you peek, the souffle collapses. The quantum souffle decoheres. And so the problem is, and the reason it's so hard, is that all of our quantum ovens leak. And so parts of the classical universe insidiously find their way into the oven and cause the souffle to collapse, unbeknownst to us. And we don't find out until later when we open the oven and we go, damn, the thing collapsed again. And what's, I think, worse is we are trying to bake a cheese souffle, and the classical universe leaks in, and when we open the oven, we discover that, in fact, we have baked a chocolate souffle. And so we will occasionally get the wrong souffle. And so this is why we have to attempt many times. And if most of the time we get a cheese souffle, we say, oh, hell, we've managed to create a recipe for a quantum cheese souffle. So I think that although I'm being glib, the basic problem is that our ability to wall off a quantum computer from the classical part of the universe and all of the interference that it provides, which has a fancy technical term called decoherence. It is an extremely difficult problem that requires some extraordinarily advanced, new, and difficult engineering in order to pull off. And we are just not there yet. And so that's why the quantum computers of today are not really ready for prime time.
I mean, that sounded very, very sci-fi.
Well, yeah, the quantum souffle, yeah, knock yourself out with that.
And I certainly will. The quantum souffle could fail for any number of reasons. The quantum states of those pesky qubits are so fragile, a slight vibration or change in temperature will make them decohere, fall out of their superposition state, and basically not be able to complete the calculation. And there is a huge amount of research going on right now to find ways to protect qubits, from supercooled fridges to vacuum chambers. And we haven't really got a definitive answer. To make matters worse, when we do a quantum calculation, we can't know the result of it until we measure the qubits or open the oven door. And doing that makes their quantum state collapse to either 1 or 0. We can't even look at the things while they're going about their quantum calculations. It's a total nightmare. So, yes, quantum computers do exist, but they're pretty limited. It's super hard to get the qubits to behave. And the more qubits you add, the more challenging it is. As researchers across the world race to design a quantum computer that works at scale, an interesting benchmark has emerged. Quantum supremacy. Which sounds pretty apocalyptic, doesn't it? Quantum supremacy is the goal of demonstrating that a quantum computer can solve a problem that no classical computer can solve in any feasible amount of time. In October 2019, Google said they had cracked it. But the team at IBM's rival quantum computing program disputed their claim. So what on earth is going on?
I would love to talk about quantum supremacy. Quantum supremacy is a worldwide attempt to solve problems, incredibly difficult problems, that no one cares about the answer to. The importance of quantum supremacy is that it is an attempt to solve a problem that is so incredibly difficult to solve with a classical computer that if you can seal off your quantum oven for a long enough period of time, and you can demonstrate that, in fact, in a short time, relatively short time, that you can solve these problems, then you've accomplished a critical engineering milestone. So quantum supremacy is about demonstrating a critical quantum computing engineering milestone, and it is not about solving problems that are of genuine, real interest from a scientific or business perspective.
Okay, but surely if we reach that milestone, we will have effectively revolutionized the world of computing.
Quantum supremacy all by itself will not revolutionize anything. What it will do is it will mark a milestone. That's literally all it will do. You know, what does a computer actually do? When you say revolutionize computing, what does that mean? It means that human beings can do something with a computer that they weren't able to do with the computer before, and it's going to have a significant impact on their lives. The fact that we revolutionize computing in and of itself is meaningless. The question is whether or not a revolutionary new computer will have an impact on humanity. And that's the only benchmark that really matters. And so the question is, what sorts of problems can we solve now because we have a working quantum computer with thousands of real, logical qubits? And how will that have an impact on us going forward? Will it result in new types of drugs that we couldn't have discovered in any other way? Will it have an impact on what we know about the universe, how we behave, how we live? And I don't know what the answers to any of those questions are. So maybe I lack vision.
Are there any problems that people are like, this is going to be perfect for a quantum computer? This is the problem that we are waiting for a quantum computer to solve?
What a quantum computer should be able to do better than a classical computer is simulate a quantum system. And a great quantum computer would allow you to simulate an arbitrary quantum system so that you could solve quantum transport problems that are incredibly difficult to solve right now, or quantum dynamical system problems that are very hard to solve right now, or ground states of more complicated molecules. But right now, I would say that there isn't a clearly identified killer app for a quantum computer. There isn't a clear problem where, with the possible exception of governments wanting to decrypt public key encryption systems, but absent that, I would say quantum chemistry is our best bet. But I don't know of a particular chemical system where everyone says, we are completely stumped by this. We have no way forward. We have got to come up with a better way, and a quantum computer would do the trick. But what I think one of the great benefits of this massive interest in quantum computing, I think it will revolutionize computing, but perhaps not in the way that people expect.
Hang on. Hold that thought, Ray. Because before we get there, I wanted to pick up on one of those threads. There's no killer application for quantum yet, so the regular organisation shouldn't have FOMO about quantum computers. But they should be paying attention to this decryption issue. Because the real reason why governments all over the world are shoveling a load of money and resources into quantum computing is because it will be able to literally break encryption. To find out more, I called up mathematician, computer scientist, and post-quantum cryptographer Sarah McCarthy.
My name is Sarah McCarthy. I'm a research fellow at the Institute for Quantum Computing, which is part of the University of Waterloo in Ontario, Canada. And I'm also a cryptographic advisor to the Silicon Valley startup QSecure. I have a master's in pure mathematics, a PhD in computer science, and I currently conduct research into lattice-based cryptography.
Can you explain why there is a bit of concern around cryptography and quantum computing?
So in the 1990s, two different algorithms were devised which enable quantum computers to solve extremely difficult mathematical problems, such as factoring large numbers. These problems are essentially unsolvable with our classical computers today. In fact, they are assumed so difficult that they're used as the mathematical underpinnings of all our existing cryptography. So if we have a quantum computer, we can break these mathematical problems and break our cryptography. So within cryptography, we have sort of two main types. There's asymmetric cryptography and symmetric cryptography. So an example of symmetric cryptography is AES. And there is a polynomial time algorithm which, when run on a quantum computer, can reduce the bit security of AES by half. So for now, we can mitigate this problem by doubling the key size of AES. So we're safe enough for the symmetric key cryptography. And in terms of asymmetric cryptography, we're not so lucky because the polynomial time algorithm called Shor's algorithm will completely break it. So this motivates the need to look at completely new types of cryptography, which is called post-quantum cryptography. And this is what I do in my work.
Okie dokie, brief encryption brush up. So you've got symmetric encryption, which uses one key for both encryption and decryption. This method was literally practiced by ancient civilizations. Nowadays, it means a quicker, simpler algorithm that's often used to transmit data in bulk. Then you've got asymmetric or public key cryptography, on the other hand, and it's considered to be more secure because it uses different keys for the encryption and the decryption process, one public and one private. The downside is it can take a bit more time. Still with me? So asymmetric encryption is used for very sensitive data. The most prominent version that we've been using basically everywhere in the world is RSA. Technically, a classical computer could break cryptography, but it would basically take forever. But for a quantum computer, well, it's a piece of cake.
A quantum computer, what it will be able to do is break the mathematics. So in RSA, the hard mathematical problem is we have two very large primes, multiply them together to get their product. The product is made public, and by having knowledge of the factors, that's your secret key or your decryption key. So if someone comes along with a quantum computer, they can easily factor, that all they need is the public key, and they can easily find out the private key. And then if they're able to do that, they'll be able to sort of eavesdrop, and they'll be able to determine the session key for all communications. So nothing will be secure anymore.
Wow. So that's quite big.
Yeah, so companies like Google and IBM and D-Wave are currently working on building quantum computers. We do not have a quantum computer which can break this yet. So we measure sort of the power, the strength of quantum computers in qubits. And right now, Google and IBM are sitting about 50, 60 qubits. In reality, we would need a 20 million qubit cryptographically relevant quantum computer, and it would take it 8 hours to break RSA. So we can see we're quite a way off from that, but there's a lot of reasons and justification for thinking about this problem now. We don't want to wait until a quantum computer is built. We need to be prepared for when that quantum computer is produced.
Yeah, so there's really no time to waste. Thankfully, the National Institute of Standards and Technology, also known as NIST, is on it. In 2016, they invited researchers to submit proposals to standardise post-quantum algorithms. The researchers have thought outside the box with a whole range of schemes based on incredibly complex mathematical structures. And the proposal that Sarah and her colleagues are analysing is in the field of lattice-based cryptography.
Lattices are abstract mathematical structures over which we can define computationally hard problems. As far as we know, these hard problems cannot be broken by a quantum computer. So we can construct cryptographic primitives over these lattices whose security is based on these hard problems. So when I say a lattice, you probably think of like a trellis type shape. So this would be a 2-dimensional lattice. But in cryptography, we are working with lattices of 512 or 1024 dimensions. So it's almost really difficult. Well, it's very difficult to imagine. But you can think of lattices as infinite arrangements of regularly spaced points. Or if you're a mathematician, you can say it is a discrete additive subgroup of r to the n, where r is the real numbers. We can define a lattice by a bunch of vectors called a basis. And this basis is not unique. We can transform the basis into a good basis or a bad basis. But both of these bases will completely define the lattice. However, with the bad basis, we only have limited functionality as to what information we can find out about that lattice. Whereas the good basis, we can solve these hard problems. It's like a trapdoor for solving the hard problems over the lattice. So the good basis is the basis that is required for secret operations.
If that's flying over your head a bit, then it makes two of us. But just stay with us.
So I'll give a simplified example of digital signatures. So let's say Alice has a message which she wants to send to Bob. She wants to sign it and send it to Bob. So she hashes or maps the message to a point in this space that's close to the lattice. And she uses her knowledge of the secret basis to find a vector or a point in the lattice which is close to this point. And this allows her to find a short vector which forms the signature. So Bob, with knowledge of the public basis, can verify that this vector is in the lattice and it is short, and hence that Alice signed the message. But Bob or anyone else who holds just the public basis would not be able to forge a signature. And some other guarantees that a digital signature gives are the integrity of the data. So if an adversary comes along and tampers with the message, the signature would no longer be valid, so Bob would not trust the message. Similarly, we have this non-repudiation technique, or this property, that says that Alice cannot deny having sent the message. And then the overall aim of a digital signature is to authenticate that Alice sent the message. And because she is the only party with the secret key, we can be confident that this is the case.
Oh my, I should have paid more attention in maths classes. But yeah, basically what I'm hearing is that the lattice is so secure that even a quantum computer wouldn't be able to crack it.
As far as we know. So this is where the research element comes into it. So if we think we've been using RSA, well, it's been around since the late 70s. So there's been a lot of time and effort to analyse it, and it's been used and it's been exposed to real world problems. But lattices have only been around for about 15 years. So we don't have that guarantee of the test of time. And at the moment, we're going on the fact that no vulnerabilities have been found as our level of trust, but we're not 100% sure that there aren't any vulnerabilities.
Once the NIST standards are published in around 2023, Sarah says vendors will start adding these standards to their products in a hybrid approach alongside existing security. That means that researchers will be able to see how this new solution fares in a multitude of real-world applications. So, how much of a risk is all of this to regular organisations?
So they're definitely going to need to overhaul their security, and they really need to act now. So there is a leader of the field, McCarthy, and he proposed this Mosca inequality to help organisations determine the quantum risk for them. So they have three variables, X, Y, Z, where X is how long do you need your information to be secure? How long will it be useful to an adversary? Or, for example, if you work in healthcare, you might be required to keep your patient data secure for a certain number of years. So this is our X. Our Y is how long will it take to migrate to this quantum safe security solution. So this might involve talking to the vendor who you get your security products from, or if you have an in-house team, and to determine how long it'll take to migrate your environment to this new setting. And then our Z is when we expect a quantum computer to be built. This could be a standard Z, but if we want to tailor it to your own business or organization, you can take a look at the threat actors. For example, if you're in government, you think, well, there's probably governments in other countries are building quantum computers right now, and as soon as they have a quantum computer, right away they'll try and break into our systems. But if you are like a local media company, it's going to take a while before anyone who who has the motivation to break into your computers has a quantum computer, as it'll be very expensive, they'll be very scarce. So again, considering how the nature of your business and where you fit within that threat landscape, you can determine your Z. How long have you got before someone is going to come along and break your encryption with a quantum computer?
You can plug your own X, Y, and Z variables into the Moscow inequality, and we'll link you up in the show notes. And you can find out if there's going to be a period of time when your information will be vulnerable. And if so, you can work out when you want to take steps to mitigate the risk. So what might those steps actually look like?
So a first step for an organisation today would be to take an inventory of their important assets, like sensitive or valuable information, and understand how it is encrypted already and how the keys are generated, how they're stored, how they're managed. The next step would be to begin building quantum safe solutions into your existing cybersecurity planning and lifecycle management. And this will give you the benefit of time to enable you to evaluate performance and functionality and iron out any compatibility issues or even update any policies and regulations. So the aim should be to address quantum risk proactively and build a roadmap now, rather than waiting until a quantum computer is built and then it's too late. Another good piece of advice is to have a dedicated team of quantum security experts, or alternatively, a relationship with an organisation who is specialising in quantum technology. You want someone who has enough understanding of the threat to contextualise the risk in your organisation's environment and to formulate an idea of the impact of these cybersecurity risks. And this works both ways because it's equally useful for us as researchers to gain exposure to real-world needs so we can steer the research in that direction.
We might not have a super powerful quantum computer just yet, but we do know that quantum computers will be able to break the encryption that we use today. This is the bit that organisations should be thinking about right now. So, we've learned why quantum computers are different, why we don't have one right now, and what's relevant to you as an organisation. But we haven't really got to the bottom of the benefits of quantum computing. Time to go back to Ray Beausoleil, who says the way that we're harnessing the quantum world for IT was summed up best by Nobel Prize-winning physicist Bill Phillips.
Bill Phillips divided quantum mechanics up into 4 domains. The Schrödinger equation is how we track how electrons move around. The Pauli exclusion principle, which says that, in particular in the case of fermions, no 2 quantum entities can be in the same state at the same time. And then there's quantum coherence. And then finally, there's entanglement. And entanglement is the secret sauce of quantum computing. It isn't enough to have the other 3. You also have to have entanglement.
According to Ray, the semiconductor and IT industry has done an amazing job of harnessing those first 2, the Schrödinger equation and the Pauli exclusion principle.
Now you could buy a piece of software that will implement classical theories of lights and quantum theories of charge carriers and simulate how a photodiode behaves, for example. It's quite common. But when it comes to how Schrödinger's equation gets used, it only gets used by the people who are first thinking about moving to the next great technology node. Like, we've gone from 12 to 7 to 5 to 3 in no time, and everyone wants to be at the smallest technology node. And the quantum mechanical simulations of how the transistors are going to behave are critical to understanding reliability and the extent to which your quantum device is in fact going to behave in a classical fashion. But then all of that quantum mechanics gets suppressed, done in a non-quantum way. And so we've continued using those first 2 principles of quantum mechanics to abstract away quantum mechanics so that we can go ahead and design classical computing.
Huh. So actually, most of the work we've done in quantum has just helped us to make better classical computers.
Now, in the case of a quantum computer, you absolutely cannot abstract away quantum mechanics. It's the essence of how the quantum computer works, and you also have to harness entanglement. The question that I have is whether or not it is possible to, in fact, harness coherence in a way that is meaningful using light to do certain types of computing, for example. And that's part of the research that we're doing in my lab and that we'll be doing more of in the future. But is there a way for us to continue to support classical computation by incorporating coherence? Right? Forget entanglement for the time being. Let's just incorporate coherence and see if there's a way for us to use it to do novel types of computing, to solve very difficult problems like the traveling salesman problem or airline scheduling or other things that plague us in our everyday lives.
Harnessing coherence sounds like pretty exciting stuff. But the most important thing for Ray is the fact that these quantum principles are going to inevitably permeate classical computing.
I think that within the next 20 years, we are going to reach a point where classical computers will need an understanding of quantum mechanics at the circuit design level in order to be successful. Now, by classical information technology, I always mean where if we have a bit, it's either 0 or 1. And it's reliably either 0 or 1. And when I set it to 0, it stays 0. If I set it to 1, it stays 1. But when you drop below a nanometer in technology resolution and you start trying to do photolithography and you start trying to localize electrons or even to count the number of silicon atoms that are in a particular gate in a CMOS circuit, you begin to get fluctuations in those numbers that are inherently quantum mechanical, and you will no longer be able to abstract away quantum mechanics. And so you'll actually have to know it. And so my hope is that all this fascination with quantum computing is going to encourage schools, undergraduate schools in engineering. Now, good undergraduate schools in physics teach quantum mechanics to undergraduates. It's part and parcel of physics now, and there's no way to avoid it. But it's rare in undergraduate classes, in electrical engineering, for example. I would like to see quantum mechanics taught to undergraduate electrical engineers, because I imagine that 20 years from now, people who are getting their PhDs currently will become research managers, for example, people who have to make decisions about the teams that they lead and the R&D they're going to pursue. And they're going to need to understand quantum mechanics in order to make those decisions, even if they're not building a quantum computer, even if what they're building is, a smartphone that has exaflop performance by then. In order to enable that, they're going to need to be building quantum circuits that can harness quantum behavior in very small features and control it. So harnessing and controlling quantum mechanics is the secret of classical information technology over the next decades. And the sooner we start educating our undergraduate and graduate students in engineering disciplines about quantum mechanics, then the more ready we will be for this eventual, I say inevitable, transition to the point where we can no longer abstract away quantum mechanics. We actually have to harness it and control it, and that means we have to understand it.
That is where we're going to be leaving today's episode. As computing components shrink, they start to collide with the quantum world. And that means that the computers of the future will work in radically different ways than they do right now, whether they're quantum computers or classical computers that exploit quantum principles. Safe to say, for most of us, this may have been a bit more of a technology entangled than technology untangled. But the bottom line is this: unless you're a scientist or engineer, you don't need to think about quantum computing just yet. But you should be thinking about the implications of post-quantum cryptography. But it might be best for you to get a mathematician to help you out on that one. Now, I don't know about you, but I'm a little bit peckish after thinking about all those mind-bending concepts. So if you'll excuse me, I've got a quantum cheese souffle to put in the oven. Oh no! It's gone everywhere! Why did I bake this? You have been listening to Technology Untangled. I'm your host, Michael Bird, and a huge thanks to today's brilliant guests, Tony Stranack, Ray Beausoleil, and Sarah McCarthy. And you can find a load of interesting links to today's episode in the show notes. This episode was written, produced, and edited by Isabel Pollard, with sound design and mixing by Alex Bennett and production support from Harry Morton, Alex Podmore, and Tom Clark. Technology Untangled is a Lower Street production for Hewlett Packard Enterprise. Thank you so much for tuning in, and we'll see you next time.